up a practice exam with a key and the Exam2 equation list have both been uploaded to the exam materials page on the website. You can look at those. The only thing I would say about the practice exam is last year's exam, and last year I did a little bit more on the different equations for all the different kinds of heat transfer, conduction, whatnot, and this year I didn't emphasize that, so that's just a little difference there. So I think there's one question on there that we might be a little bit it's something we haven't talked about at all, but there we go. And what I wanted to do first is talk about that last homework problem on homework. So you should have been able to do that homework problem because, as the hint said, it was almost identical to example problem, but I want you to understand it. So essentially, it all hinges on this sort of consumption rate. So this reaction rate we've been learning about for the last week or so. If you multiply it by the volume of your reactor, you get this consumption rate that we know from back when we were doing balances. Okay? And so if you want to find the volume of a reactor you need, it just looks like this. That right there is the key to that homework problem you did. Okay. So in this case, the case of that, I believe this was the reaction rate, but it could be anything. So you'll have a reaction rate down here on the bottom that depends on the concentrations of your reactants. Okay, so if you want to find the volume you need for your reactor, you'll want to know two things, this rate of consumption and the rate of reaction. So this rate of consumption here, this is in units of moles per time, and you can find this from a mole balance. So if this was the last test, and you didn't know that any of this other stuff was in your future, and I asked you to find the rate of consumption of whatever, you would know how to do it. You would just do a mole balance. Okay? And then this, and then you would also have to find the reaction rate, which means finding the concentrations of the reactants, because reaction rate depends on the concentrations of the reactants. So these concentrations, if we have, let's say we have a reactor, stuff goes in and out. Are those concentrations the concentration in the inlet streams or the outlet streams? Outlet streams, if this is a CSTR, because we assume it's well mixed, and so then the concentration inside the reactor, which is what controls the reaction rate, is the same as the outlet. And so that big, long problem that you did on your homework, in the end, it just boils down to this. It boils down to you have to do this, and therefore you need to find the rate of consumption of, in that case it was butadiene, and then you have to find the outlet concentrations of the reactants to get the reaction rate. That's what that whole big problem boiled down to. And so this is important. I added this relationship to the equation list. We did talk about it in class, but because both of these use a little r, I can see why it would be hard. It's important to keep them straight. So yes, so this one has units of moles per time. This one has units of moles per time volume. Okay. Any questions about that? Okay, so now I'm going to go back and cover what we did. So first things first, don't forget the first half of class. The first half of this class did not disappear. So I still expect you on the exam to need to know things about, well, for example, let's say you have density and volumetric flow rate, and you need to find, or not density, concentration, and you need to find the molar flow rate. How would you do it? Multiply them. Or if you have the molar flow rate and you have the molecular weight, and you need to get the mass flow rate. Okay, so all those kinds of things. Or mole balances. I won't do any tricky mole balances. No tricks. It'll be simple. But yeah, you may need to do mole balances. Okay. Then we talked. So we started this section talking about fluid flow. The most important thing to remember there is, of course, the mechanical energy balance. All right, you should know what every term in here means. Okay, you need to be able to, with a simple problem, set this up and know what to cancel out. We had one day about pumps, and we had a pumps lab also. And so you should know the difference between this little WS and this big WS. What is the difference between this little WS that's in this equation here and this big WS? Yes. The big one is power. In your lab, you calculated power. Okay. So yeah, so in the lab, you calculated power, which is energy per time. What are the units of like watts? What are the units of little WS? Energy per mass. Every term in here is units of energy per mass. Okay, so that's just something to understand. Okay. Yes, but for solving, yes. WS is positive for a pump. And it is negative for a turbine, however you pronounce it. Okay? And if we go through and we think about it, this makes sense. A pump puts energy into our fluid, and a turbine takes energy out. That's also why this minus WF term is negative, is taking energy out. Yes?
What were the values for alpha?
The values for alpha, so most of the time we assume turbulent or rough flow, and then alpha is 1. For laminar or smooth flow, alpha is 2. This was the case in your lab, and I told you I'll always tell you if that's the case. Hiram, yes.
Okay. Yeah, I'm gonna ask, if we're using a turbine, would we equal negative negative W? Right now, it's a negative WF.
Yes, negative WF.
So if we're using a turbine, would we constantly?
No, it would not. So the WF is friction.
Oh, sorry, WF.
Yeah, so WS is the shaft work. So if it's a turbine, okay, let's see. Well, it depends on what's happening. Let's say if I give you the setup and I give you everything except for WS, and then you and it's a turbine, and you solve for WS, the answer you get should be negative. It should be a negative whatever.
But the symbol stays positive.
The symbol stays positive. And then I might tell you something like, if I told you something like, let's say I gave you everything except for the pressure out or something, and I told you that we have a turbine, and the turbine extracts 1,000 joules per kilogram from the system, you would put in negative 1,000 right in there. Okay. All right, so I guess I would say the symbol stays positive, but you put a negative number in it. Okay? Then we talked about heat transfer for a while. I want you to know the difference between the modes of heat transfer: convection, conduction, radiation. I need you to know the difference between these two equations and when you use them. Okay, so if we have a liquid turning into a vapor, which of these do we use? The one on the right. If we have a vapor turning into a liquid, which one do we use? The one on the right. Any phase change. If there's no phase change, then we use this guy, and the temperature changes instead. So if we have a vapor turning into a liquid, let's say it's water. So we have steam turning into liquid water. From the point of view of the water, is the heat flow positive or negative? Negative. I heard negative. Why negative? Okay. I saw someone make a hand gesture and then nod and say yes. So why is it negative?
So because the transfer from hot to cold, and the water is cold and the
Well, okay, so he said the water is colder and the steam is hotter. It would be more accurate to say the water is lower energy. Okay, same idea, but they'll actually be the same temperature right there on either side of the phase transition, but the water is lower energy. And so when the steam turns into liquid water, energy leaves it. It turns into water. That is why it is negative from its point of view. We also talked a bit about heat exchangers, mostly conceptually, but we had this one important equation here, which you can use to size a heat exchanger. We had a homework problem where you needed to do so. So this heat duty there, how would you find the heat duty of a heat exchanger? How did you do it on your homework? Alright, on your homework, you use this one. So a heat exchanger always has a hot stream next to a cold stream. Okay, and heat will go from one to the other. And so the heat of each stream is going to change. Either their temperature will change or their phase will change. And then you use these ones to figure out how, yes.
Is that a negative sign from us to use?
No, that was a little dash.
Makes more sense.
Yeah. I'll do a bullet point instead. Okay. Yes,
Was there an equation that we learned that had U naught in it, or was that?
that was the only one we learned. And this is a general equation almost any heat exchanger will do, but the only one we looked at, the one we did a homework problem on, was a very simple one called a countercurrent heat exchanger, where you have hot in here and cold in here, and they run counter to each other. Okay, and then finally, reactions and reactors. We learned, what a reaction is. What speeds up, slows down reactions. We learned of rate laws of this form. Like that. Okay, so review. We made a couple assumptions when I told you we were going to be using rate laws that look like this. What were they? It's one way, it's irreversible. What was the other one?
First order.
So if it's first order, then M and N will be 1. And most of the ones we've used have been first order, but they could be other things. The other thing we said is that it's in the liquid phase. Liquid phase, irreversible. And what will the units of this rate of reaction be? Now, we just talked about this at the beginning of class about the homework problem. What will the units of this rate of reaction be? Moles per time volume. So that if you multiply it by the volume of the reactor, what do you get? Moles per time. Yes?
When you say it has to be a liquid, do just the reactants have to be a liquid, or all of the chemical species, like all of the?
So, if it's essentially irreversible, then it shouldn't matter if the products are gases, I don't think. It's, yes, I don't think it would.
Because wouldn't that change the volume of your reaction?
So, it depends. If, let's say if your reactants are dissolved in water, so like in your lab, both of you had crystal violet as a reactant, and then you have sodium hydroxide as a reactant, and both of them are dissolved in water. So even if they end up turning into some gas and bubbling off, you still have all of that water left behind. Most of the time it probably wouldn't change the density, volume, or I'll just say it depends.
So basically just the reactants have to be liquids.
The reactants have to be liquids if it's irreversible. Yeah, irreversible reactants, liquids, you can use those. It's mostly your thermodynamics class when you're going to learn about all of the complications there, like what to do when it's a liquid versus a gas versus if volume changes, all of those things. That's something you learn in thermodynamics class, where you sort of learn, you very much learn about how the different states of matter and the way things can be will change the energy of things to change how reactions happen. Yes?
Could you go over how to work with non-first order?
Sure. So, it should be pretty simple. Let's take, for example, let's say if we have a reaction that's 2A plus 2B goes to like A2B2 or something. Okay, and let's say this is, I'm going to say this is an elementary reaction, which means that we didn't talk a little bit about that, but let's say that the reaction rate is this. Okay, so that's very much something that could happen. So how does this change what we've done? If you figure out, for example, if you figure out that Ca is 0.5 moles per liter and Cb is 1 moles per liter, okay, and then K, so let's think about this. We know that the rate of reaction, those units should be moles per liter time, let's say seconds in this case. And this are going to be moles per liter squared times mole per liter squared. So, can anyone tell me then what the units of the rate constant have to be? Okay. I heard liters cubed per moles cubed second. So what people did there is they looked and they saw what the units there had to be in order to cancel out and leave you here. So in this case, this will cancel out everything except for 1 mole per liter over here, and you will get moles per liter second is equal to moles per liter second. So that's the main thing that will change, is that the units of the reaction rate constant will need to change in order to get this out. So if I give you a reaction rate constant for something like that, it will have the right units. So let's say for this one, okay, so that's the concentration of A, that's the concentration of B, and let's say that K is 2,000 liters cubed per mole cubed second. So how about you all calculate the reaction rate for me? That's better. Okay, since you asked the problem, could you also calculate it? I want to make sure you can do it. Okay, does someone have an answer? 500? 500 moles per liter second. Okay. Yes.
And how would we know if it's first or second order?
I would have to tell you.
Okay.
Like, being able to figure that out is an advanced skill that you have not learned, I would just tell you. Yes?
So are most of the reactions we're dealing with just first order?
The ones I've given you are, so far, I don't want to tell you what will be on this test. I'll always tell you, I think at least that part will be very straightforward. I don't want to trick you or make you try to figure it out or anything like that. But once you have the reaction, you should just be able to plug in the concentrations and the reaction rate constant and get the reaction rate. Yes?
So where's the equation sheet for the exam?
It should be up, give me a second to check and make sure. Okay, it's not up, I'll put it up. Yeah. I'll put up the equation sheet. Alright. It will also be a little different from the one last year, so I'll put up the one for this year. And you will know what you have. Again, I don't think memorizing equations is all that important, which is why I give you an equation sheet. Things I don't put on there are things I think of as not really equations, because they're such basic relationships. That's why I'm never gonna give you, I'm never gonna give you n times molecular weight is equal to n, because I see that as such a basic relationship that's not really an equation. Okay. And, so with this guy, what if we had a reactor? Let's say we just have our reactor is just like a 500 milliliter flask. Right, and we have tubes coming in and out. Let's say that's our reactor. So then what would the rate of consumption of A be? Okay, so we just figured out the reaction rate here. I told you that the reaction is taking place in a 500 milliliter flask. So what is the rate of consumption of A? $250 milliliters. And how did you get 250, moles per second, sorry. 250 moles per second. How did you get 250 moles per second?
Well, you know that 500 milliliters is half a liter, so you take half of 500.
Yeah. And he said you take half of 500, or if we were just to write it out, we would say the rate of consumption of A is the rate of reaction of A times the volume. So it would be 500 moles per liter second times half a liter, 250 moles per second. Okay, so, yes?
What makes something a second order reaction?
So this one here, this is second order with respect to A and second order with respect to B. The order refers to that exponent there in the concentrations. It refers to how it relates to the concentration of that reactant. So this would be fourth order overall, second order respect to A, second order respect to B. So, and to think of that as sort of words, you would say if this reaction is second order with respect to A, that means it depends on the square of the concentration of A. So obviously the higher order it is, the bigger the effect of changing the concentration is going to be. On a practical level, as I said, I'm always going to tell you, we haven't, not ever gonna try to trick you with this because we haven't talked about a lot and you don't really know how to figure out what the order of reaction should be on your own, so. Someone who's done this lab this week, in the lab you know the volume of the reactor, and we have you figure out what the concentration of A and the concentration of B is. And so what do you find then? What is your final thing that you find? You find the rate constant in the end. And it's the same thing, like you figure out the rate of the consumption. And you figure out the volume, so then you can figure out what the rate of reaction is. And then you can find the rate constant. Okay, questions? Yes?
So, we talked a little bit about in lecture about KR star.
Mm-hmm.
I didn't seem to see too much in the textbook about that. Is that gonna be on our test?
It could be, but I would always make it very clear if it was. But let's talk about KR star. If, let's say we have some reaction that is rate, reaction, and then we say that the concentration of B is much, much greater than the concentration of A, then we can assume that CB is about constant, and then we can define KR star, that's just KR times CB. Okay, so if this was on the test, I would make it very, very obvious. I would just tell you that the concentration of B is much, much larger than the concentration of A, so we can assume it's constant. Yes?
So KR star is related just to this kind of situation where one of the concentrations is negligible.
Yeah. Yeah. One of the concentration changes is negligible, yes. That's when we use KR star. KR star is notation that says that one of our concentrations is constant, so we can just lump it inside here and make one constant. Yes?
Is that the first order reactions and the second order reactions?
So if it was second order reactions, let's say, okay, so let's say our rate of reaction was KCA CB squared, so it's second order with respect to B, and CB is about constant. In that case, KR star would be KR CB squared. Because if the concentration of B is about constant, so is the concentration of B squared. B squared constant, you get it's constant, right? On the other hand, if our reaction rate was K, like this. So now it's second order with respect to A, first order with respect to B. B is the one we're assuming is constant. Then KR star, what's KR star? KRCB. Okay, because CB is the one that's constant. And then rate of reaction would just be KR star CA squared. Like that. Okay. So all of these things, if they're different order, I probably should have given you some more examples of those, because I sense you're intimidated by them, and you shouldn't be, because it's actually very easy. You just use the same equations and you just square things or cube them or whatever. So that's why I should have given you more examples like that. Okay. Yes.
Can we always use the delta t log mean for any
Okay. In this class, yes. So delta t log mean is a way of getting an average delta t between the hot and cold streams of a heat exchanger, which you always have to do. And the delta T log mean you learned was for a single pass countercurrent heat exchanger, which is a very simple case, and it's the only one we're going to use in this class ever. So if you had more different heat exchangers, more unusual ones, or more complicated ones, you might need some other way of finding an average temperature difference to go in that equation. We will always just use delta T log mean. Yes.
As long as you're consistent, it doesn't matter what changing.
What 1 and 2 is? Yes, as long as you're consistent, it should be, right? So one of these will be smaller than the other. And so if your delta T1 is smaller than your delta T2, then on top here, this will be negative, because you'll have a smaller thing minus a bigger thing. And then this will be negative, because you'll have a natural log of a number less than 1. Okay, so negative on top, negative on bottom turns into a positive. And then if it was the other way around, right, you would if delta T was greater, 1 was greater than delta T2, then you would get a positive on the top, because a bigger number is smaller than a smaller number, minus a smaller number. And on the bottom, you would get a positive, because you would have a natural log of a number greater than 1. So it would be a positive. And so if you're consistent, then you should come out with the same number, and it should be positive. Okay. Yes?
One more question about the Arrhenius equation. Do we have to know that?
Okay, so I did not emphasize it very much in class. I'm putting it on your equation sheet, but I'm going to go ahead and tell you you're not going to do any calculations with this. You haven't done any calculations with this so far. The main thing about the Arrhenius equation, which, as a reminder, gives us okay, you didn't do any calculations with it in your homework or in class, so I'm not going to expect you to do any calculations with it on the test. Okay, I'm going to go ahead and tell you everything you do on a test is the same kind of thing you've done in homework or in class. Like there might be, I might make some little tweak to it that if you understand what the problem is, you'll be able to change, but it will all be the same species of stuff we've done before. So you won't have to do any calculations with it. The important thing to remember here is that this shows how the rate constant changes with activation energy and with temperature. So with temperature, when temperature goes up, how does the rate constant change? It goes up, it gets bigger, When temperature goes down, what happens to the rate constant? It gets smaller. When the activation energy goes down, for example, if you add a catalyst, what happens to the rate constant? It goes up, it gets bigger. Okay, all of those things, they make the reaction go faster, and they make the reaction go faster by changing the rate constant, making the rate constant bigger. So that's the important thing to remember from this equation, not having to do problems with it. Okay, we have 4 minutes, so maybe one big question or 2 small questions I can answer in this time. Yes.
Which topic do you think students struggle with the most on this test?
Let's see. So all of the reactor stuff, it's what we did last. So on the one hand, you haven't had as much time to think about it, but you also haven't had time to forget it. The fluid flow, most students are pretty okay with it because it's similar to some things they've done, though. Having to deal with the WS and the right signs for that, a lot of people forget about that. So I'd say probably the heat transfer stuff, because it's kind of in the middle. We covered it a couple weeks ago, so it's not as fresh as all of the reaction stuff, but also it's not quite as familiar as just Bernoulli's equation. Though, yeah. Knowing, I would also suggest, I'm going to put the video for the last class, the reactor design class. I think that's probably one people just have the hardest time getting their head around. The video of that will be going up, and it's also, we covered stuff in here in class that isn't really covered in depth in the book. Partly we do that to make sure you can understand your lab. So I would encourage going over the slides and maybe even watching the video of the lecture for that, because there's information there that isn't covered in depth in your book. Yes?
Will there be a practice test on ionic?
Yes, there's a practice test on ionic already posted. I haven't posted the equation list yet, but I will do that as well. Yes?
Will we need to know about residence time?
Well, you need to know about residence time. Probably not. We didn't do lots of calculations for that. You don't have to practice. I would like to maybe kind of know that in general, bigger residence time means more reactions, but yes. I'll post this. Yeah, I'll post this, what I just wrote today. Sure, I can post it. It kind of wanders around, but hopefully it'll be helpful. Yeah, so I'll post that on Ionic as well. So the page is called Exam Materials. If I were you, I might also look at the key for Exam 1. Just look over it, as I said, so we don't forget the important stuff from the first half of class. Okay.